everyone. This is Zhongwen. Today is August 12, 2020. In today's video, I'm going to go through the research item progress since the past week. So as you can see from the Gantt progress bar, we still have 2 items in the stack. For the first item, to extend the survey to the general version, the progress is estimated to be about 4% in the past week. And for the deep learning workflow, the progress is about 3%. Let's get into detail. For the first item, after a carefully read, the newly written sections recently I put on the paper, including the goals, requirements, and challenges. After I read through them, I found these sections are pretty raw and rough. So I tried to rephrase carefully, line by line, section by section, and even add something more to each paragraph. I still work on this one, and also I refined some of the sections in the last section, the AI, but I'm still working on them. Hopefully by the end of this week or early next week, I will be able to handle a better version to Dr. Liu and Dr. Che, so they are able to help to review and keep refining the paper. So that is the first item. So let's get into the second. The second is that I added the correct CCS code for the paper that is required by the ACM publications. So if you take a look at the paper, you will notice that at the top of the paper, we will be able to include some keywords. So from here, we need to include some CCS concepts. And these concepts are basically, we need to find the concept ID and the description as well as the significance that we specify for each of them. But the ID should be fixed. And also we need to list the description at the bottom. So this is a place where I find this CCS code, including ID. Basically, I will check any of them and try to assign them into the CCS. So maybe I will assign them with the high relevance or medium or low relevance, and then add to the CCS concepts. After that, I will be able to generate the code. So if you can see, I generate the code. It will include all the sections I've been adding just now. So you are able to see that. So I can copy and paste this one to the paper. So that's how we generate the CCS code from the ACM website. And furthermore, I refined the pseudocode, the description of WRPS, because it's still accordance to the previous pseudocode. But we made some change to make it better, and I refined that and include the line code as well. And for the second item, the deep learning workflow, currently I'm trying to construct the convolutional layer. And I said that before in the previous video, I'm trying to stack more layers on this simple example, because this one only have a linear layer, neural layer, and a ReLU layer, and a sigmoid layer. But after I carefully go through the code, and I think it's not feasible to add more meaningful layers. For example, for the linear layer, the input is only 2-dimension array. So if we insert another linear layer in the middle, it will not work, because input will require only have two items or 2 neurons input. So this will not be able to extend further or be tested further. So otherwise we need to construct new layers. So that's why I'm currently thinking about the convolution layer is very important for now, because we want to construct a new network in soon work, including some role detection, for example, work. So that will be a very big progress or milestone in order to make that happen. So there are 2 ways actually to write the convolution layer on GPU. So the first way is we can write from the pure CUDA. And basically we will need to implement a forward propagation, and this is very simple, and backward propagation. And after I check a little bit on the website, I found that there is not too much information about backward propagation in the convolution layer, because most people is only care about the forward. They don't care about how we do the backward. And I found few resources I'm currently reading through. And basically this is one of the example that goes through the back propagation in the convolutional layer. And basically we're going to update the inputs. Also this is a derivative will be propagating to the previous layer, and then we will update the weights because we have a filter, and we will update the weights of the filter, and we will also update the bias for the convolutional layer. So this is pretty similar to other layers. We will times the inputs with the weights and plus a bias in order to get a forward propagation. So this is a forward propagation, but for the back propagation, it's a little bit different because we have to go through to get the derivative for x, w, and b respectively. So the dx will be propagated to the previous layer, and dw will be used to update the weights of the filter, and then we will do the update on the bias as well. So I haven't complete the explanation, or I haven't complete this post because I still be there's some dangling mathematical explanation. I have roughly go through all of them, but I think there's still be several places I will still be confused. But in short, it's very the back propagation for the dx is simply like another convolutional operation. So basically we'll do the convolutional on the dy. This is a derivative that propagate to this layer, and then do the convolution between this one and the w. W is a weight. So here is an example of the one-dimensional convolution back propagation. And the derivative of the derivative of the dw and d bias will be very simple. And currently I'm going through the multi-dimensional examples. I found I still be some confused about some part of them, but we'll keep work on that in order to make that clear, and hopefully will be more clear soon. So this is the first way. I also read some other resources. Maybe we will need to implement the techniques like the momentum, because the convolutional neural net layer is also need a momentum for most of the time. So maybe we have to implement that as well. So this is the first way, implement by pure CUDA, and the second way is to implement by the CUDNN. So this is a CUDA neural network library. So that is built by the NVIDIA, and the same thing is still work with CUDA, but we will have some existing neural network library can be worked with. So I think this is a good tool as well, because every other, like the TensorFlow, they also use a CUDA as well as a CUDA CNN. PyTorch, they also use a CUDA and CUDA CNN. So I think this is a good library to move forward. So basically, currently I'm reading the documentation of the CUDA CNN. So I think it's pretty similar, or it's just like a method that's written based on the CUDA, and we still need to do the memory allocation. So here's one example of the CUDA implementation, CUDN implementation on the convolutional layer. And basically we still need to do the same CUDA thing. For example, we need to allocate the memory, and we need to clean the memory, such as CUDA malloc. We have to use a CUDA to allocate the memory and copy the memory and memory set as well. So most of things will be same, but we will have some library can be used. But this post only implement the forward propagation. It does not have the backward. But if we take a look at documentation, actually it includes the forward and backward propagation for most of layers. Not all of layers, I would say. So I think for most of layers, they have the forward and backward, and I think this will be easier to work with. I will also read through the documentation and try to analyze which way is better, and so I think in this way, if we use a CUDNN, work with CUDA, and that will be easier if we want to extend our application with momentum and other methods or techniques in the neural network in the future. So I think this is beneficial as well because CUDNN is built for the CUDA, especially for the neural network. So I think this might be a good way to move forward, but I will still looking forward and look into and see if it is true. So I think that's pretty much from my side for the past week. I think I didn't move super fast, so I also spent some time in other things. But I hope this is good so far. This progress is good so far. So thank you so much for your time to watch this video, and hope you enjoy it. Until next time, happy coding.